Good morning, Year 12. We are now moving on to a Year 13 topic. I think in normal times we would have spent a bit longer on our Year 12 organic topics, but I think the wrapping up of all of that requires us really to be not doing this remotely. So we're going to be moving on to some Year 13 chemistry. So the first thing we're going to be doing is optical or stereoisomerism, sometimes also called chirality. So lots and lots of new language, I'm afraid, with this one. So this is quite different from the isomerism you've seen before. So it's not about moving atoms around, it's about the 3D structure of molecules. So the things we're going to run through is what is chirality or stereoisomerism or optical isomerism, why it's important, identifying chiral carbons, and how we represent enantiomers with diagrams. So I'll explain what the word enantiomers means in a bit. So what is chirality? So chirality it really comes down to whether, if we take this molecule here of methane, which I've built here with one of the monomods, is its mirror image non-superimposable? So that's some quite complex language, but it's language you need to know, so we're going to make a note of this. So it's about whether it's got a superimposable mirror image. So methane here, this does have a superimposable mirror image. So what that means, if I take the methane and I sort of do the mirror image of it, so the mirror image is this here. So we've got a mirror plane down the middle. So running down the middle, we can imagine a mirror plane. Think back to like your Key Stage 2 maths lessons where you got the mirrors out. You put the mirror down in between, have to draw either side. Now these two molecules are exactly the same. They are superimposable, so I can sort of overlay them upon each other and they could occupy exactly the same space. So if you made almost like a mould for this, both of these could slot into that same mould, or it's like fitting a hand into a glove, it would go in correctly. Now speaking of hands and gloves, hands are not superimposable mirror images. So if I take my left hand, my right hand, at least to an approximation, is a mirror image of it. However, if I overlay them with each other, right, the thumbs are on the wrong side, they're not superimposable. I could flip my hand over to make it on the same side, but it's still not exactly the same shape. So they are not a superimposable mirror image. I have prepared a molecule that does not have a superimposable mirror image. So this molecule here, it's just a bunch of colours and they don't necessarily represent any particular atom. Now if I do the mirror image of it, so I've got a mirror plane down the middle, these two molecules are not exactly the same. So if I try and overlay them on each other and get the oranges and the purples lined up, but the green and the white don't overlay with each other, they're not superimposable. So this molecule is chiral. It displays optical isomerism, whereas methane is achiral or non-chiral. It does not show optical isomerism. So our sort of definition we can say is a chiral molecule has non-superimposable mirror images. I just realised that should be imposable, not able. So that's our sort of definition for what chiral is. You need to know that. And so we had our left and right hand is the sort of classic example of it. So we'll do a bit more of a dive into that later, but why it's important. So chemically, if we were just looking at this as a sort of pure chemist that had nothing to do with any biology, these really are very similar to each other. These two molecules are going to display almost exactly the same chemistry. They're almost completely indistinguishable from each other. When it does matter is when you get into the realm of biology, and chemistry overlaps a lot with that. If we take, for example, thalidomide. Now thalidomide has a rather checkered history, as it's caused an awful lot of harm. Now, it was given as a morning sickness drug to pregnant women. So morning sickness is where some women, when they're pregnant, feel really, really nauseous a lot of the time. And so thalidomide was developed and it was an incredibly effective drug. It was really, really great at treating the morning sickness. Now, thalidomide is a chiral molecule. It has the R and the S version. These are the labels we give, like E and Z for the molecules. So the two different versions, sort of the right-handed and the left-handed. The S actually stands for sinistra, which comes from sinister, which is what either the Greeks or the Roman or Latin for what left-handed is. So left-handed people apparently are sinister. Now, the R-thalidomide this is actually the molecule that is biologically active. This is the one that treated the morning sickness. Now, S-thalidomide, however, is something called tetragenic. Now, tetragenic is things. It interferes with the development of developing organisms. It causes mutations in them, and pregnant women, which this was given to, happens to have a developing organism inside them, and so their babies were born horribly mutilated. Generally, they lost all their limbs, so they were born without limbs or very stunted limbs. And quite unfortunately, a large number of people were born in like the 70s or the 60s, born horribly mutilated because of the S-thalidomide. And the drug thalidomide was sold as a 50-50 mixture of the two versions, R and S thalidomide. So, this mixture, this 50-50 mixture, this has a specific term that you need to know, which is called a racemic mixture. So, a 50-50 mixture and this is where we need to bring in this word enantiomers. So these are enantiomers of each other's. Or this is the R enantiomer and this is the S enantiomer. So a 50-50 mixture of the two enantiomers is called a racemic mixture. So this is another really important definition that you need to know. So you need to know this term racemic mixture. It's a 50-50 mixture of the two enantiomers. So this is the R enantiomer, this is the S enantiomer. We might say that these are enantiomers of each other. This is one enantiomer, this is the other enantiomer. I can't be bothered to work out which one's R and S. Right, so this one, this is no longer used. This is actually sold under a different name. This is just like a drug name. It's not the actual systematic name for it. This is sold, I think it's used as a leprosy treatment, for which it's very effective. And because they no longer sell the S-thalidomide, they're not allowed to sell a racemic mixture anymore. The drug rules were changed to that really no new drugs were allowed to be sold as a racemic mixture. They have to be pure of one enantiomer. We sometimes call that enantio pure, to prevent things like this ever happening again. Now, the reason why chirality has why they say the different enantiomers have this effect is that the way most drugs work is by interfering with an enzyme in some way. So they're generally going to slot into the active site of a molecule, of an enzyme, sorry. Now those enzymes, they have a complex 3D structure, and so the shape might be complementary to one molecule, so to one of the enantiomers, and so it slots in and it has the desired effect on the desired enzyme. Now the other molecule, it's not going to fit into that shape. They're very, 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 very similar, but it has a different 3D structure, and so it won't slot into that enzyme. So it might just sit there and do nothing, or it might interfere. It might interact with a completely different enzyme that you don't want to interact with, that's really, really vital, interferes with it and causes really serious harm, which is what would have been the case with the S-thalidomide. Okay, so we've gone over what is chirality, why it's important. We're now going to look at how we identify chiral carbons. So this is spotting molecules that display chirality, and then identifying the carbon that's responsible for that. And so in most molecules that are chiral, it's going to be down to a carbon, and all the ones you're going to see at A level, they're all because of a chiral carbon. So there's a little rule that we can use to make it fairly easy, I think, to identify where that chiral carbon, or chiral centre as it's sometimes referred to, is found. And what we're looking for is simply, we're looking for a carbon bonded to 4 different groups. No, not 4 different atoms, 4 different groups. So you could have 2 different carbon chains and they would still count as different groups. So in that case, the carbon would still be bonded to 2 carbons, but because those carbons it's attached to have different things on it, they're not exactly the same. So let's look at an example. So if we take so we have here butan 2R.